So, many a times we find lot of difficulties in finding the exact roots of certain equations. Today, we are going to discuss how to get the approximate value for the roots of some equation. So, before getting into that, let us start with a very simple problem uh, that compute the approximate value of square root of 17. So, we will use differential calculus to address this problem. Consider the function f of x is equal to square root of x. Now, for x strictly positive, we know that f is differentiable. Therefore, for any x naught greater than 0, we have f prime of x naught, this is equal to limit x goes to x naught f of x minus f of x naught divided by x minus of x naught. So, now for value of x close to x naught, we can write that f prime of x naught is approximately f of x minus f of x naught by x minus of x naught, where x is close to x naught. If we solve this equation, then what we are going to get is that f of x is approximately equal to f of x naught plus x minus of x naught into f prime of x naught. Now, for our particular problem of square root of 17, consider x naught, let us say, to be 16. So, then square root of 17, which is equal to f of 17, which is square root of 16 plus 17 minus 16 into f prime of x naught is f prime of x, we have calculated that 1 by 2 square root of x. So, 1 by 2 square root of 16. This is equal to 4 plus 1 into 1 by 2 into 4, which is equal to 4.125. If you use calculator, you can find that the correct value of square root of 17 is 4.123. So, that means by taking x naught to be 16, we are very close to square root of 17, and the error what we are considering is 0.002, which is a very marginal error even if we are considering our starting point to be x 16. Now, let us try to apply differential calculus for other problems. You see, if we have a quadratic equation, then we know, or a cubic equation, we know quadratic equation we can factorize and we can find the roots. Such kind of formula are also available for equations with third degree and fourth degree. However, when we encounter with equation more than fifth degree polynomial, then there is no such formulas available to us. Then the question is that how we are going to find a root. Suppose, for example, if I take x polynomial of order 5, then what we have seen as an application of initial value theorem, that there exists a real root. Now, the question is that how we are going to capture that real root. It may be extremely difficult. Here is a method which is basically given by Newton, which suggests us to get approximate root. So, and also if we consider, so suppose we have this x to the power 5 plus 7 x square plus 21 x plus 6 is equal to 0. How to find a root of this? Root of the, not only this algebraic equation or polynomial equation involving polynomial, we also encounter with some equation which are transcendental in nature. For example, find x such that cos x is equal to x. We know that if you draw the graph of cos x and if you draw the graph of x, they are going to meet. So, this is going to, so how to find this root? So, these are the type of questions we are going to address today. Okay, so, now what is Newton's method? Let us see that this is a function. So, we are interested in finding this root r. Now, what we take is that we choose some x 1, then this point is x 1 f of x 1. Now, I draw a tangent line. So, this meets, let us say, at x 2. Now, I have this point which is x 2 f of x 2. Now, I draw a tangent at x 2 f of x 2. So, I am going to get into x 3. This tangent line cut x axis at the point x 3. So, I consider here x 3 f of x 3, then again I draw a tangent which is going to cut x axis at x 4. So, if I repeat this process, I can keep on going this process, and these extends many a times. For n large, they are going closer and closer to x to the root r. So, what does it mathematically say? Now, consider y is equal to f of x. Now, the slope of, and f is differentiable, that is important, slope of tangent at x 1 f of x 1, this is equal to is f prime of x 1, this is what we know. Now, we are interested to find the equation of this line. So, now what is x 2? So, x 2 is the tangent. Let me draw the picture. Suppose this is x 1 f of x 1, then this one is x 2. This is x 2 and 0. So, now what is this x 2? Now, this x 2 is the tangent line touching x axis. Now, what is the equation of the tangent line? That means, this is the equation of the line passing through x 1 f of x 1 and x 2 0 with the slope f prime of x 1. So, we can find that out. So, therefore, we get x 2 is equal to x 1 minus f of x 1 divided by f prime of x 1. So, provided this f prime of x 1 is not equal to 0. So, similarly, now I take f of x 2. So, the equation, rather slope of tangent at x 2 f of x 2 is f prime of x 2. So, the point this tangent is going to touch the x axis can be written down like this. So, x 3 is equal to x 2 minus of right. So, we can continue like this. So, what we get is x n is equal to x n minus 1 minus of f of x n minus of 1 by f prime of x n minus 1. So, this method is called as a Newton's method, or sometimes in literature you will find that Newton-Raphson method. So, what it says is that basically for large n, x n is close to the root r. So, before working out some example, let us see certain remark. Suppose for example, here we always assumes that f prime of x n is not equal to 0. Now, when it is close to 0, now let us see that we are interested in finding the root of this y equal to f of x. Now, suppose if I take my x 1 here, then this is x 1 f of x 1. Now, if I draw the tangent, then this is going to be my x 2. Now, this is what is x 2 f of x 2. Now, if I draw the tangent, then this is going to so this is going to be my x 3. Now, you can see that now x 3 is lying outside the domain of f. So, we cannot even define f of x 3. So, this sort of thing may occur, because here this f prime of x 1 is pretty much close to 0. Therefore, we are having a problem. So, if we get into this sort of problem, so how to avoid that? So, we need in these cases we need better choice of x 1. So, now with this remark, let us calculate some concrete example. Find third approximate root of the equation starting with x 1 is equal to 2. Okay. So, now consider what is our function here. Consider f of x, which is equal to x cube minus 2 x minus 5, and f prime of x, this is equal to 3 x square minus of 2. Now, x 1 is equal to 2. Now, x 2 is equal to x 1 minus f of x 1 divided by f prime of x 1. which is equal to 2 minus f of x 1 is 8 minus 4 minus 5 divided by 3 into 4 is 12 minus 2, which is equal to 2 plus 1 by 10, which is equal to 2.1. Now, x 3 is equal to x 2 minus f of x 2 divided by f prime of x 2, which is equal to 2.1 minus 2.1 cube minus 2 into 2.1 minus 5 divided by 3 into 2.1 square minus 2. Now, if we calculate this, this is going to be 2.1 minus 9.261 minus 4.2 minus 5 divided by 3 into 4.41 minus of 2, which is equal to 2.1 minus, this is 9.2. So, therefore, what you are going to get is 0.061 divided by 12.41 minus 2 is 10.41. Now, this is going to be 2.1 minus approximately, which is equal to 0.0054. So, which is equal to 2.0946. In fact, if you find root of this f of this equation, then up to 4th degree this is correct. So, with the third approximation we could reach up to the correct place up to 4th degree. So, the error term would be 0.0000 and something, 4 zeros and something. So, this is a very powerful tool to find the roots of various polynomials. In most of the cases we cannot factorize it, we do not have a formula to find the roots. So, therefore, this method comes very handy. Now, let us try to see some transcendental equation as we discussed at the beginning. So, consider cos x is equal to x, find x up to three decimal places. That means what? So, this is correct up to we can. So, this means we are going to apply Newton's method and we will stop at the stage where we get the repetition of the first 3 decimal places. So, let f of x is equal to cos x minus of x. As what we are interested in? We are interested in finding x such that f of x is equal to 0. Now, f prime of x, this is equal to minus of sin x minus of 1. Now, let us start with let x 1, the first approximation is 1. Now, x 2, this is going to be 1 plus cos 1 minus of 1 divided by 1 plus sin 1, because minus of f of x by f prime of x. So, this is rather for the, it will be better if I write it in this form. This is x 1 minus f x 1 by f prime of x 1, which is equal to x 1 we have taken it to be 1 minus cos x minus of x divided by minus sin x minus 1 minus become, this is sin x plus 1. Okay. So, now this x 1 is 1. So, I can write down this cos 1 minus 1, then this is sin 1. So, this if we do the cos 1, then this is approximately what the value would be 0.540 minus of 1 divided by sin 1 will be 0.841. This is approximate value up to 3 decimal. So, now this you can, this is 1 minus 0.46 divided by 1.841. So, which if you calculate, this is going to be 0.7501. Now, we will find x 3. X 3 is going to be x 2 minus f of x 2 by f prime of x 2. So, if you put that, then you are going to get 0.7501 plus then cos 0.7501 minus of 1 divided by 0.7501, and this is 1 plus sin 0.7501. So, which is approximately equal to what you can get is that 0.7501 minus 0.011, then which is 0.7391. Now, if you calculate x 4 by putting this, that means 0.7391 plus this cos minus 0.7391 divided by 1 plus sin 0.7391. So, which is approximately you are again going to get that this is 0.7391. So, this is where we are going to stop, because we are interested in finding up to correct 3 decimal places. So, we have got the repetition of 0.739. So, up to 3 decimal places, the x having 0.739 is going to be a root of the equation cos x is equal to x. So, this as you can see that this is, it is very difficult to find the root of cos x equal to x, but this method suggests that, I mean, some approximation up to correct 3 decimal places. If you want to get it more, then you consider here the more decimal places, then up to, suppose you want to find up to 8, correct up to 8 decimal places, then you keep on calculating. Whenever the first 8 they match, then you stop. Here from x 3 to x 4, these two are matching. So, we are stopping here. So, similarly, depending on the number of decimal places you want to get the correct solution, you have to continue with this process. So, and this is an application of differential calculus. So, in the next lecture, we are going to discuss integration. Thank you.